we'll go over the diverging lens. Diverging lenses are shaped somewhat like this. This one is shown much thicker than it actually would be. And it has an axis through the center and also a horizontal axis or optical axis. Just like the converging lenses, diverging lenses have a focal point, which would be the same on either side. But they're a little bit different in how they work. So if we have a horizontal light ray coming through to this diverging lens, it will exit the lens as if it came from the focal point on the same side from which it entered. So it's going to fan out on this side. So if we brought in another horizontal light beam, we'd bring it into the center, and then again we would connect the focal point and it would exit that way. Same thing if it's below the axis. Come in this way to the center of the lens, and then it would exit as if it was coming from that focal point. So they in general function like that. The rays diverge. They get further apart as they go away from the lens. We will work through On Your Own 1210 so we can demonstrate a couple of these principles. On Your Own 1210 says we have a diverging lens with focal points that are 8 centimeters from its center. So we'll go ahead and draw the lens. We'll mark the center. And we'll draw in an optical axis, which would be perpendicular to that center. And we'll mark our focal points, 8 centimeters out. On Your Own 12.10 says, if we have an object that is 5 centimeters from the lens, how will the object appear? So this is very similar to the converging lens problem that we just did, but it's an opposite kind of lens. It's a diverging lens. We're going to draw our object there. And again, we'll show we have an eye over here, which is looking at this. So we can imagine how this is going to work. All right, there's our eye and my great artwork. So just like the converging lenses and the mirrors, we have 3 specific rays that we want to draw. The first one we will draw, because it fits a nice pattern, is to bring one in that's horizontal or parallel to the optical axis. So that's our first line. We bring that into the center of the lens, and then that one will exit as if it was coming from the focal point. So we line up the focal point with the center of the lens here, and we'll extend that light ray, and we will extrapolate that backwards as well, shown by the dashed line here. So that's our first light ray. The second light ray is the partner to that one, and that one we will draw as if it is headed to the focal point on the other side. And that one will exit the lens horizontally. And we'll extrapolate that one backwards as well. You can see that my parallel lines were a little less than parallel. Use your imagination. The third line that we will draw with the third color is the easiest one. It touches the top of the image. It goes right through the center of the lens, and it does not get deflected on its way out. Alright, so in all of that tangled mess, we can tell that the actual light rays do not intersect. But if we look back here, this actual light ray and this extrapolated ray and this extrapolated ray, they do intersect right here, and we would call that the image point. And we would put the tip of our image right there, and the tail of it would sit on the axis just like the tail of the object. So in this case, we can look at this and we can say, is it real or is it virtual? Well, since we used extrapolated light rays, it is virtual. We would ask ourselves, is it inverted or upright? And obviously it is upright. And the third question, is it magnified or reduced? It is smaller than the original object, so it is reduced. So if you were looking through this lens at this object, it would look smaller than the actual object.